Okay, thank you very much for the invitation. And I hope you hear me well on Zoom. I assume in the room everybody hears me. Yes.
Yeah, I can hear you well.
Okay, thank you. Ricardo is recording? No. I don't see that. Go on more. Okay. Give me back the... Okay, so the initial idea I had in mind for these two talks was to discuss about sources, mainly. And because before the first detection of gravitational waves, there have been a lot of work discussing various possible sources of gravitational waves, which include, of course, binary coalescence, which is all what we've seen so far, basically, but also other stuff like non-symmetric rotating stars, supernovae, cosmological backgrounds, etc. And then, of course, the detection and the many detections by LIGO, everybody was on coalescences, compact binary coalescence. Then now I think it's time to remind ourselves that there is other stuff to look for, and some of which maybe it has already been detected, as I will argue in a minute. So that was the initial idea, and then I realized that I cannot do that in a meaningful way without discussing possible way of detections, because some of the sources cannot be detected with the current instruments. And so they became detectors and sources, when the word detectors has to be taken really in a broad sense, okay? Detector is anything which gives us evidence of gravitational waves. And so the thing will be naturally split into two parts. I will discuss detectors in a broad sense today, and on Monday we will really go into sources. And okay, let's start just for as an invitation. I know I'm just changing page here, not on my. Okay, so this is the evidences we have of gravitational waves existence so far. We start from in historical order from the Hastello pulsar and other pulsars. So in that case, basically we have any spiraling binary who is losing energy in a way which is perfectly compatible and predicted by gravitational wave emissions. And how do we know that this binary system is losing energy? Is that because we measure the period is shrinking. And we know that the period is shrinking because it happens by chance that one of the two components of the binary, which is in our galaxy some 6 kiloparsec away from here, one of the components is a pulsar. And just as a reminder, the pulsar is what is left after some branch of evolution of a star. It becomes a neutron star. It has a strong magnetic field, and it emits a ray of particles of light in a given direction, but this ray is not aligned with the rotation axis, so it does really like a lighthouse. And in some cases we are lucky enough that this lighthouse is, in its precession, is passing through Earth, and so we see regular flashes of this object. And some classes of pulsars, which are the millisecond pulsars, you may switch it off, otherwise we can have an echo. Okay, some classes of pulsars are really, really precise. They are fantastic clocks. And so, by measuring this pulse, the clock on this pulsar, which is in the binary system, we can see it moving around the orbit with the other binary components, because some flashes arrive before, some flashes arrive later, and that gives us the idea of the movement of this object. And this has been done for 20 past more years, and you see this is the prediction for the period variation. Now, the second evidence in order of time is in this plot below. You might be familiar with the symmetric version of this, where the highest mass black holes are in the center here, and there are some more or less masses in the sides, but I like it more like that. That is, of course, coming from LIGO collaboration. You can go on the website, and it's public. You can just play and arrange the events as they are. And here we are talking about coalescing binaries. Okay, before it was a spiraling binary. The two stars in the Hart-Taylor system are compact, but still far apart. They are not coalescing any time before 200 million years, while these objects are really coalescing while happening. And well, we will discuss that next time, but on Monday. But you see there are more than 100. Basically, the blue things are black holes. So it's most of all black hole binaries of a mass of some ranging around 10 up to 100 solar masses. And the little dots, I mean, you can ignore the yellow and red. They are just electromagnetic things. They don't have anything to do with gravitational waves. While the orange things are supposed to be neutron stars. And so there are a few candidate neutron star coalescence. One of them is very famous because it has been detected both in the gravitational waves and in the electromagnetic thing. Okay, that's the second evidence, but we'll discuss that more in detail on Monday. And the third evidence is pretty recent, basically 1 year old. It is a result of the observation of more than 20 years, and it comes also from pulsars arrays. Pulsars arrays are, I mean, we still have pulsars like in the Hart-Taylor, but these are not in binary systems. They are just still around the galaxy, around here. And basically what we measure is, again, through the pulses, the variation of the distance or of the time that the pulse takes to arrive to us, and we can deduce in a very clever way the passage of gravitational waves from here passing in between us and the pulsars. The origin of these gravitational waves is not clear. It might be probably some supermassive black holes during some spiral, or it might be something more cosmological in the sense of modern gravitational waves of cosmological origin, maybe during inflation. We don't know yet the answer. You see the error bars here are pretty large, and it's not possible to say that. But okay, all in all, that is very evidence we have so far. If I come back, if you invite me back here in 15 years, maybe this slide will look like this. So I see I added more stuff. Some of this is made up of basically taken from some simulations. We will discuss this stuff in detail, but the bottom line is that going on from now, we don't expect just more of the same, okay? Instead of 100 coalescence, we will have, 100,000, good, very good. But there will be also really new stuff, and this is the ultimate reason of this talk, is to walk through these other possibilities.
So what are you not commenting about the other plots?
We will see them through the, probably more on Monday, okay? But this one, will have something on by the end of the talk. Okay, it was just to see that there is more to expect, and this is why we are here today. So, okay, even before going into real business, Just let's agree ourselves about what a gravitational wave is. It's a metric perturbation, and I can, if I point here, they will not see that in Zoom, right? If I point here, so I can point here. Basically, metric perturbation, in principle, you have 10 degrees of freedom. You get rid of 4, choosing a system of coordinate or a gauge. That makes out 4. For example, the most popular one is this one. And then you, from the Einstein equation plus this gauge choice, basically the equation for the wave become, I forgot an H here, a trace of H here, become this. So it is an equation for the remaining 6 degrees of freedom. It turns out that out of these 6, 4 are entirely constrained by the energy momentum tensor, like, for instance, Newton potential. Newton potential is a small perturbation of a metric, yes, but it's not a gravitational wave because it doesn't propagate like a gravitational wave, but it is in this 4 thing, and some 2 real gravitational waves, okay, which propagate like a wave. And we will discuss about generation, how they're generated on Monday. For the moment, we are interested in the detection, so we just like to know how they propagate from the source to us. So in the propagation equation, we can just set this to 0, and basically the equation becomes a wave equation, what else? And we can just arrange coordinate, the residual coordinate choice freedom to have this the waveform having this shape, for instance, okay, the TT part. And we have a 2 polarization, so this is the fact that the wave entering in the screen has on a set of free falling masses. I'm going pretty fast here because I think you know what I'm talking about, so let's not stay more on that. So now I will give you or derive for each class of detector a sensitivity of a detector, okay? Its capability to detect and its sensitivity to detect gravitational waves. And that is, I have to go over some definitions because when I give you sensitivity, it doesn't make any sense alone. There are conventions, because basically everything we work out is a signal to noise ratio. It has a signal part and a noise part. With iteration, I can put some stuff in the denominator or not, and sometimes it is convenient to have some conventions, some other, it is convenient to have other conventions. So let's get this thing straight here. And so whenever I will give you a sensitivity, I will mean a convention. So on Monday, when we give you a strength of a signal, we will remember that I use the same convention, and we can compare the two, and we can superimpose that on the plot and see what can be seen, what can be not, and under which conditions. So the basic idea is that you have your detector, which has an output, in which part, one part called H is not a gravitational wave itself, it's some quantity which has been processed and depends, let's say, linearly on the gravitational wave, plus another part which is basically the noise of the detector. For the noise of the detector, it is usually assumed that it is Gaussian and stationary, which bring to the relation which I wrote here. So it is statistical properties are entirely in this approximation, characterized by the so-called strain, by the so-called noise density function, which is equivalent to say, I mean, this statement and these two statements on the sides are exactly the same, just to give you the meaning of this Sn. Normally we are in a situation in which this H is much smaller than the N, but we can extract it if we know the shape of a signal through the match filtering that consists in multiplying my output by a given function in order which resembles much to our signal and extract the information. The philosophy is that if this K looks like H, when I multiply this part, I will have a signal which is more or less constant, and when I multiply by this, since this is random, it will fluctuate, So if you stay a long time enough, the signal will come out. Okay. Of course, sometimes you cannot stay as long as you wish because the signal is short. That is part of life. And okay, this is the philosophy of mismatch filtering, and you can do it in Fourier transform. And it turns out that the best filter you can use, that is the one which gives you the largest signal to noise ratio, has this shape, which is pretty natural. Okay, you want to mimic your signal as good as you can, but you better do it very well when your detector is sensitive. Because if you do it where the detector has already a lot of noise, you're gaining not that much. Okay, so this is a reason of this ratio. And then you can compute given this filter, you can compute the signal to noise ratio. So this is a signal to noise ratio after you have done the filtering already, otherwise it will be hopeless normally. And it has this shape, okay? Now I can just say, okay, this is the signal, this is the noise. The convention, which is usually, especially for binary coalescence, is to write this in logarithmic terms. So the f is f d log f. And then you take the remaining f here, right? Okay? And so the ratio is this one, okay? So when I give you the sensitivity of the detector, which is basically the square root of this Sn, it has not to be compared to the Fourier transform of the signal, but there is an f inside. Okay? That takes partially into account the fact that if you have a periodic signal, you stay, if you have many cycles, so if f is large, you can integrate for many cycles and you gain signal to noise ratio. There are other conventions. For instance, you can multiply both sides by f, so you have f squared here and f downstairs. That gives you to another notion of sensitivity. It depends on what convention you use, but we have to know that. Okay. Normally, for LIGO, this is what it is plotted. Okay. It is the square root of this, which is the dimension of 1 over square root of Hertz. That is the convention I will use. And this works perfectly well for signals like the coalescence. Okay, so a short signal which is very well featured, we know everything about it, and that is what we are plotting normally. There are some cases in which this formula needs to be specified a bit, and we are going to go through this now. So, for instance, if your signal is periodic, then all of this becomes a little bit meaningless because you have to replace with a delta. And of course, in a very real experimental situation, you are not following your signal for an infinite amount of time. The experiment has a duration. And so here the signal to noise ratio becomes basically the amplitude in a real space of your signal times the time of observation. Okay, so the signal to noise ratio, this is squared, but the signal to noise ratio grows like the square root of observation time. Or basically the square root of the cycles you have, right? Because observation time is proportional to how many cycles you have. Okay, and that is also valid for the spiral part of the coalescence. If you observe a lot of cycles and you have a good filtering, you are improving, you're boosting up your SNR, so your detection chances, by the square root of a number of cycles. And it is worth noting here that, again, it's in this ratio you can use different conventions to distinguish the noise and the signal, the sensitivity of the signal. In LIGO, Virgo, what is usually taken as noise and sensitivity is just Sn, like before, which makes sense because which makes sense when you are observing a coalescence, right? Because it lasts not that much, and in a given period you expect your detector to be always the same. Okay, so you keep physically, intuitively, it makes sense to have this fixed. That means that when I give you the expected signal for a periodic source, that will grow like the square root of time. So it's not the signal itself which grows for the periodic, but I'm telling you that if I observe there the signal for a lot of time, your signal will go up. Okay? It is also possible to think in the other way, that the signal is fixed. After all, your signal is a signal, and it is sensitivity which goes down. So you define the sensitivity like Sn over t, and with the observation time, the sensitivity goes down. This is not what we do in LIGO, because in LIGO, the sensitivity, it's practical to have it fixed, because you observe both in spirals and also coalescence, and maybe what else. While we will see for the pulsar arrays, the convention is the opposite. So you have the signal which is fixed and the sensitivity which goes down. But the fact is this, okay? Bottom line, whenever you have a periodic signal and you want to compute the signal-to-noise ratio, you better tell me the observation time. 1 year, 2 years, 5 years, because it really depends on it. Similarly, but in a different way, when you have when your signal is the gravitational wave signal is a stochastic one. What do I mean by stochastic? I mean anything which is not produced by one single resolved source, but by many sources, so many that you lose track of it, so you better treat it as a random variable. Okay. In this case, then also your h of t becomes a random variable. You have to treat it in the same way as you treat the noise. Here a means anything which I haven't written, maybe the wave number, the polarization, anything you could be interested. So the correlation must be some delta times again some noise spectral density, this time of a signal, not of a noise. And for a single detector, the SNR is basically the ratio of the two. So there are no tricks. You cannot do match filtering with anything because we don't know what it is. And so if you have just one detector, you just switch it on. You think you know what the noise will be for your detector. If you have more, if you see more stuff, it must be the relational way. It's not a super good strategy, and it's not also very promising in terms of result. What you actually do in this case, you have two detectors, and basically you correlate the output of the two detectors. Both they contain a part of gravitational wave, stochastic, and a part of noise. But the part of gravitational wave, you expect it to be correlated if the detectors are close enough or arranged in a particular way, while the noise, each detector is supposed to have its own noise. So in the end, again, if you have enough time, the correlation should win over time. And here is the final formula for the signal-to-noise ratio. Squared, again it grows with time. It has basically, again, as you expect, the ratio of the spectral density of a signal divided by the spectral density of the noise, times this function, which basically is a generic geometric function which takes into account how two the detector overlaps. Yes?
So the noise here, you assume it's like from earthquakes and things like that?
Anything, yeah. Yeah.
But I mean, it's different from when we're looking for a certain wave, right?
It's different from what?
When we're looking for a gravitational wave?
Yes.
For instance, for a periodic signal,
Uh-huh.
the noise would, for instance, the stochastic background would be a noise for that periodic, right?
Oh, yes, okay.
So
That's a complication of
what's
that.
the noise here? Because we're kind of measuring the noise.
I'm assuming that the things are separated, okay? And yeah, I mean, the noise is just instrumental noise, and this problem will be relevant for laser, and we will see that. But we don't expect that to happen, for example, in LIGO. Yeah, it's a good point, but let's make this simple. and we'll discuss that maybe later. So, okay, we have a ratio of the two spectral densities times a geometrical factor which takes into account how the two detectors are disposed geometrically, okay? And
you want to say something more about the overlap function?
not really, just that, of course, if they are far apart, f, the maximum reasonable frequency which you have overlap is just 1 over the distance. If you are too much far apart, you don't have too much overlap. And so on. And okay, also another useful variable for the stochastics is the density of energy in gravitational waves, which is related to this SH just by this factor. I just mentioned it because maybe we are going to use it later on. So, okay, now that is what it is more than enough that I have to say. I have half an hour to sweep over the detectors. So let's start from the interferometers. Basically, like you can see the first picture, that is effect of a light in free-falling objects for a given polarization. And what you're measuring here is really the variation of distance, of two distances, the orthogonal, for instance, by the passage of a gravitational wave. Or better, since you're measuring the distance with light, you are measuring the light propagation time back and forth for the two arms of interferometer. And just basically, how do I write to this formula? You set this to 0, because light is what it does, and then you integrate it on this path from here to here and back, and from here to here and back. And since there is a gravitational wave here, you have the integration of the gravitational wave. That is basically what you're doing. Now, in theory. In practice, there is, for instance, in normal interferometers, a lot of complications. You choose to do it with a laser. So you actually don't measure the arrival times. You measure the difference, the phase shift between the two beams which go in different directions, which is not exactly the arrival time. It has a similar relation, which also involves the gravitational wave. And then, since the arm of your interferometer is just a few kilometers, you want it longer, because the longer it enhances the sensitivity. You build Fabry-Perot cavities, which is basically a way to have effectively a light path of 100 kilometers, but compactified in an object which is just a few kilometers. And there is a lot of stuff which I'm not going to discuss, but because I want in the end to end up with the sensitivity. And the sensitivity, basically, for current experiments, is the one which I plot here. I'm plotting the quantity square root of Sn, right? Here. And you see, we are about 404, basically 10 to minus 23, something like that, in the ballpark of around 100 Hertz. Again, this is not the amplitude of the waves. Looks like, because by chance, you have to multiply or divide by f, square root of f, and f here is more or less 1, so you're not that far. But we see for other experiments we taking place at much lower frequencies, this number can be very different. But remember, when you have to translate it in the amplitude in time domain of the gravitational wave, you have to decide which signal you're talking about, how much you're looking at it, and then you can have a number. Okay? So that is the sensitivity. This is just a map of the existing detectors, you know, the two LIGO and Virgo, which are here, and the new one, Kagra, which is this one in Japan. This is a time frame of the runs which has been done so far. 3 runs completed by LIGO, then Virgo joined in O2, just in time to see the double. O1 was the first detection, the O2 was the time of the first detection of the double binary little star. And then during O3, tens more of black hole binaries. And we are just in the middle here, in the gap between the two parts of O4. O4 already started, LIGO alone. And now there is just a break, and in 1 week, Riccardo tells me, then we start again to take data, and Kagra will possibly join in the end of the run. And okay, will be a low 5. This is a plot already shown. The importance of Kaga is that it is kind of in between this generation of detectors and the new ones, in the sense that they put it underground, which is supposed to be, which effectively reduces the seismic noise, and they are using cryogenic optics, which also reduces the noise related to the optics. This technology will massively employed in the next generation of ground-based detectors, like Einstein telescope and the Cosmic Explorer, which are planned but not completely funded yet. So, caution here, but they are supposed to be running in the late 30s. The philosophy is basically do the same as LIGO or in Virgo, but larger, deeper underground, cooler in the sense that cryogenic. Okay, the two will explore different direction in this philosophy. For instance, the Cosmic Explorer will be larger, 40 kilometers. The Einstein telescope will be a bit larger, around 10, 15 kilometers, but will be underground. And I think both will be cryogenic. Very try. And as a result, the sensitivity curve will be in the same, more or less, in the same frequency range, but a bit smaller. You see, I mean, not a bit. It's another of magnitude. Another of magnitude, since the gravitational wave scale like 1 over the distance. Another of magnitude is in the strain, is 100 of magnitude in the amplitude, which is another of magnitude in the distance, which is a factor of 1,000 in the value, and also in the rate of what you expect. Okay, so if there have been 100 observations in LIGO so far, you can expect to be 1,000 more from this object, provided that there is stuff to see.
1,000 times.
1,000 times, yes.
So also it's not only going down, but it's also wider.
Yes, good observation. That is effect of going underground. You reduce the seismic noise, which is the limiting factor at low frequencies, and the cryogenic should help lowering this curve at high frequencies. So yeah, there is really a lot of improvement. The other detector, LISA, sorry. It's still an interferometer, but this is not even an interferometer. You still have arms. You have these 3 satellites which are orbiting, following the Earth. And the satellites are here. Basically, the Earth will be around here. They are following the Earth in an orbit around the Sun, and they are free. And we measure again the distance, the variation of the distance with the 2. But you cannot do it in the same way as an interferometer, just using the same difference, the phase difference between the lasers, because on a separation of 5 million kilometers, which is the arm length in this case, we are using, you don't have laser which can allow you such measurement. What you instead you do is you send pulses at regular intervals, and you measure the difference in the arrival time. It's the same, you just a different use. It is more, in this equation, it is more related directly to this thing rather than the phase difference. But in the end, the result is more or less the same. I would like to spend a lot of time on that, but I don't think I can. So the sensitivity, so the square root of S, which is the same quantity here, will have more or less the same shape, but it will be centered around 10 minus 3, 10 minus 2 hertz, because the arm is larger, and the sensitivity will be more or less 10 minus 21. Okay.
You know what makes the noise curve go up and low and high frequency?
I was just working myself this morning. I don't know. Not the observation time. The ultimate. No, that is that is on the lower end. The lower end, the ultimate limit is observation time, but for LISA it will be 10 to minus 8. But this is going up, so I don't know. I will check maybe for Monday. No, now, in the last 20 minutes, I want to come to the really new stuff. That is maybe stuff that you don't know that much. First, the pulsar timing array, and the second, the cosmic microwave background. So, pulsar timing arrays, basically, you're still measuring distances and pulses, but this time you don't have an interferometer, you have single arms, and the arm is constituted by pulsars, like the Hubble, but they are not in binaries, they are isolated. They must be, because in binary that would be MS, I will explain you in a minute. So these pulsars are also on super clock, very precise. They send us pulses at regular time, every millisecond or so. And if a gravitational wave passes by, it will change the distance, and as we argued before, we will have a different arrival time for the pulse. Okay? I had adapted the previous formula to this case. So for a single pulse, you have the observation. You observe the pulse when it is emitted, plus the distance in units of speed of light, plus the perturbation given by the passage of gravitational wave. Now, the quantities which you actually are interested in is the variation of the frequencies. Okay, so you just measure the difference between two pulses, which is basically one of the period of the pulsar, and you just see how regular they are. And basically, so you can just simplify this formula and go it down in this case. You can replace this. The derivative is basically because you're measuring the first pulse arises this time, the second pulse arises 1 millisecond later, and so you have the gravitational wave at a given time and a millisecond later. Since you're speaking of gravitational waves which have a very low frequency, the difference is not that much, so you can replace it by the time derivative. And that's why basically this formula is here, because the period of a pulsar of a clock is much smaller than the period of the sampling that you're doing is much smaller than the period of a gravitational wave. Actually, you're not even measuring Z, you're measuring the residual, which is the integral of Z over time, but let's keep this part. The point is that now I can compute, plug in my age, and since the main target of this is a gravitational background, you don't resolve the sources, we plug in the gravitational wave background, so we basically know this about our gravitational wave, and so instead of using the correlator, the single arm, you can use a correlator between the signal measured in one pulsar and another arm, okay? And you plug in this formula, you insert this in the relevant point, you do all the integrals, etc., and basically you can express that for two, given a pair of pulsars, the correlation of this residual, of this variation of the arrival time of the pulses is proportional to the stochastic quantity which gives you the power density of in this gravitational wave signal, times a geometric factor which only depends on the angle between the two pulsars. Okay? And this is really remarkable. It doesn't matter where they are, but there is a universal function of this angle. And this universal function is computable here. I can plot it here. And that is exactly the function which I have shown you at the beginning. Okay? And now, if you adjust two pulsars and you just try to do this experiment, the error bars will be enormous, because the pulses themselves are not regular. Every pulsar there is no sort of noise, and there is experimental error involved. So for a pair of pulsars, it's very problematic to extract a signal from that, because the error bars will be huge. But what this experiment do is that they have a collection of 100 of pulsars around the galaxy here in the nearby. So they can do this. So say 100 pulsars makes more or less 10 to the 3, 10 to the 4 independent pairs. you can pair one with the other in all possible way. Okay, you should just not take too many because they are not independent, but that makes a lot of pairs. And then if you have a lot of pairs, you can really sum up the signal, and what is left is what I showed you in this picture here. So the error bars are kind of small enough to give you a hint that something is going on here. Okay, what is it? Now, I done the calculation for the stochastic background, meaning that this is a sort, this contains a sort of average around the relevant direction of the pulsar. Now, if you have we don't know if you're looking at what you're looking at is a stochastic background or it is a signal for a single supermassive black hole, which is given this. In order to do that, we should the difference between the two comes from the fact that if you have just one single source, it will affect the different pulsars in a different way. Because I can write it maybe. Now you are here, it's us. There is pulsar A, there is pulsar B, okay? If a gravitational wave travels here, this pair is affected, maximally you say, because the distance is shrinking in this direction. If a gravitational wave is moving here, in this direction, the effect will be not that much, because it is transverse, so this length will not change that much. So, all the pair of pulsars will have a correlation which goes like that, but if a signal is coming from a given single direction, so it is anisotropic in the sky, some of them will be more affected, that means the effective SH here will be larger, and some of them will be less affected. There will be a geometric effect.
That C of theta doesn't depend on the direction of arrival of the gravitation.
Because I'm in the hypothesis of a stochastic background, so the C of theta includes an average. Okay, so you should just extract from this this function plus times a geometrical factor. That will be the answer, okay? And geometrical factor could be different from each pair of pulsars depending on their orientation with respect to the gravitational wave. Of course, if you have a background of gravitational waves coming from everywhere, it doesn't matter where the pulsar, the pair is oriented, the result will be the same for all of them. So, maybe in the future, when the error bars will be smaller, we will be able to see whether the signal is coming from a given direction or if it just is isotropic. If it is coming from a given direction, it might be one or two supermassive black holes in spiraling. We will discuss that on Monday. If it is homogeneous, we don't know what it is. It could be a lot of supermassive black holes, or it could be a background of originated in inflation or cosmological origin, and that we don't know. Okay? So at this moment, we don't.
What is a lot that discriminate between a few and
it depends on how we will be able to reduce the errors.
Yeah, but
in the moment, a lot is one because you don't know.
Yes, but I mean, then, but you know how you're reducing the error. You're reducing the square root of time.
And add it more pulsars.
Yes, but there are not so many pulsars. What? No?
I don't know.
Suppose you just increase with the square root of time.
Then it's going to be hard, I think, because they're already taking this from. This is the result of 30 years of observation. So if you wait another 30 years, you get down by a factor of 2.
No. Square
No?
root, 6, no, 5, 6 square root. Ah, no, 2, yeah.
With respect to now.
Yes.
So just counting more time is not doesn't look very good. You really should have tried to have more pulsars, more statistics. Okay, so I'm almost on time to discuss the cosmological microwave background. I will not spend time telling what it is, okay? Last scattering surface, when photons start to be entangled with the free electrons and protons which are around, and they start to move freely, and they are allied to us. It is highly isotropic, and it has small fluctuation on top of it. And the way they're plotted, so this is a map in a sphere, okay, in the 4D sphere, And this is the translation in the so-called coefficient CL, and it is useful to remind where this comes from. So this is the temperature. You build a map. Okay, you measure the intensity of radiation coming from all direction. You build a map of so this temperature fluctuation as a function of a sphere coordinates, and you can expand them in a base of the function of the sphere, which is harmonic spherical harmonics. So there's these coefficients, and these CL are basically the correlator of these coefficients. Okay, these are the ones which are plotted here. Now, the correlator means a statistical ensemble. We don't have many universes, so the trick is replace the correlator here by the sum over the same L of a different ALM. Because since the radiation is highly isotropic, you assume that the different AMs are basically different realization of the same thing. So you can replace this by this object. So this is an estimator of the object, which is so this is a theoretical object, and this is the estimator, and these are okay, perfect agreement given the model, etc., etc. That is so far from the temperature fluctuation. What is the effect of a gravitational wave or temperature fluctuation? In equations, you basically have to solve the propagation equation for a null geodesic. P mu is the impulse of a photon, and then you solve for P0, which is the energy, because the thing that you measure. You plug in here in the gamma, there is the gravitational wave, and you solve it, and this is the result. Physically, this is a part of what is called the integrated Sachs-Walsh effect, which basically says what follows. If you have your photon traveling to us, and it goes in a potential well, suppose there is a star or something like that, it will gain energy here, it will lose energy here, and in the end it will realize the same thing. But if this potential is time dependent, so maybe it's the star is collapsing or something like that, so during the time it will be deeper. So when the photon enters here, it's blue shifted, and while it's here, the hole has become deeper, and when it comes up, it is shifted more. Okay, so in the end, the final energy is smaller than the energy it had before entering the potential one. This affects anything, scalar perturbation, I mean star collapse, etc., and also the passage of the gravitational wave. Okay, so the photon arriving to us meets gravitational waves. They are time dependent. Sometimes it will be redshifted, sometimes not. And in the end, this is an effect of the temperature of the final energy of the photon. From this, you can already understand that the frequency which are ascending here are very small frequencies, corresponding to very large wavelength, because if a photon crosses a gravitational wave with a very large frequency, in the end, the effect will average to zero, more or less. While if a photon has to cross path with a gravitational wave which has a wavelength like that, and which changes 1 or 2 times during the time it takes for us, so from the last scattering surface to here, then the effect will be enhanced. Okay, so we are speaking of frequencies more or less 1 over the distance from us to the last scattering surfaces, which is basically the age of the universe. Okay, they're very low frequencies. This is the object we're talking about. But as long as the temperature fluctuation are concerned, there is no reasonable hope to see them in the cosmological microwave background, because it is dominated by other fluctuations, by scalar fluctuations. Okay, like when given by Newton potential of collapsing objects, etc., etc. So, or scalar cosmological perturbations. The calculation has been done. Scalar perturbation dominate over tensor, and we are not going to see that. But what is useful and will help us to find to detect gravitational wave perturbation is the polarization. Okay, the cosmic microwave background do not measure just the energy of the photon coming, they measure the polarization. And so basically you have to consider the whole, not just the intensity of the field, but the whole field, including the polarization tensor. And you can build a polarization tensor from your incoming photon field. Now this is a tensor, and a tensor which is traceless, asymmetric, and so the notation is that this A, B, and C, they live on a sphere, on a two-sphere. And G and B is the metric of the sphere, but it's not really relevant. I just have a polarization tensor, and I want to use the same treatment which I used for the temperature, which is a scalar. So the nice thing is that this tensor, which is symmetric and traceless, can be decomposed into gradients of a scalar or rotor of a scalar, something like that. Okay, like the electric field can be written as a gradient of an electric potential, for instance. So a scalar function gives you a vector. In the same way, this quantity can be reduced to the study of two quantities, AE and AB, which are called the electric and magnetic, but there's nothing to do with that, just the way they transform another parity. The electric and magnetic component of the polarization tensor, which if you know the polarization tensor are given by that. So in the end you can measure this thing. So now the question is how the polarization tensor is affected by the gravitational wave. And for this thing we have to know, that is a formula, but the formula doesn't tell that much. You have to know first, two things. First of all, the CMB photons are polarized. That is because the scattering, the cross-section of photon of an electron is proportional to the scalar product of the two photons, the incoming and the outgoing. Okay? So suppose you have a scattering like that, incoming photon, outgoing photon. The cross-section depends on this object. So if you have a photon which is polarized in this way, orthogonal to the plane of scattering, then this thing, and so the probability of having something here polarized in this way, in this case, the polarization is, this factor is always 1, so it's constant, does not depend on the angle, okay? While if you have a photon which is polarized in this way, in the plane, you know, on the plane of scattering, then the probability of a photon coming out in this way is strictly 0, while the probability of a photon coming out polarized again on the plane of scattering depends on the angle. Okay? It will be maximal in this direction, and it will be strictly 0 in this direction, because if the direction is pi half, this direction and this direction will be parallel, will be orthogonal. Okay. So as a result, if you have photons, an unpolarized beam of photons, you will have coming out more stuff polarized in the direction orthogonal to the scattering plane, and a little bit less stuff polarized no, actually, yes. Okay, there is a difference, okay? Now, if this is for a given incoming direction. Now, if you have isotropic photons coming from every directions, then the thing will compensate, okay? Because the photon coming from here, and the same photon coming from here, and from here, everything will compensate. But if, on the beginning, your photon field has an isotropy, in particular a quadruple anisotropy, there will be more stuff coming from some direction than from the orthogonal, and then the difference will be, in the net polarization will be not zero, okay? This is what affects the problem here. So you have a temperature anisotropy at the beginning in the last scattering surface. So at let's say a temporal anisotropy here, sorry, around here, there is a temperature anisotropy, okay? Then there is a scattering, the photon is scattered because there are, from the moment the photon is decoupled to the moment where matter is recombines, not ionized, there are still ions around. It can scatter and ionized to us, which are here, okay? So it's a process in two steps. First, the photon is emitted. Immediately, after a little bit, it encounters a free electron. And since this free electron receives an radiation which is anisotropic at the beginning, the final outcome is polarized. Okay?
Yeah, but I mean, the radiation comes from all over. How come this effect doesn't average out?
No, the radiation comes from here.
Yes.
Yeah.
You mean the photon?
Yes.
Yes, you see the photon.
Yes.
But the gravitational radiation, I mean, is stochastic.
This one?
No, you
No.
get photons all the time.
Yes. First, they are emitted from here, and they all arrive here where there is this electron. And since this is not isotropic,
Yes.
to begin with,
Okay.
the outcome will be polarized.
Okay.
Okay.
No, but heuristically, how do you arrange specific polarization? Okay, this is just stochastic. I mean, you have some amount of polarization.
Yeah.
Just by chance.
Yeah, of course. And so, yes.
Isn't it helpful? Like, I don't know if you have a source, scattering, you have a source here, rotation wave scattering, and the source has, I don't know, some particle momentum, particle momentum, and because the source has a different particle momentum, it will scatter more or less, depending on the direction.
The particle momentum of the source is induced by the gravitational wave. No, that's the point.
Part of it.
Yes.
I'm not speaking gravitational wave for the moment. I'm just saying that if the radiation here is a quadrupolar component, that will affect the polarization of it will give a net polarization of the incoming photon.
It's crucial for the source, the matter thing, to be anisotropic.
Yes, this has to be anisotropic.
Yes.
Otherwise, the net effect will be cancelled. Okay. So, all in all, you plug everything in the formula, and that is the result. So this is what happens here. The delta T is here, and then the other stuff is propagation effect, and the S is a geometrical effect given by these definitions. Okay, and in the end, you have your polarization, and in delta T, you have to plug in the previous formula. Okay. For the propagation, not before it was from here to here, now it is from here to here. But it is the same formula. And then in the end, we just arrive at this plot. Now, the gravitational wave, so I have my polarization tensor PAB. It has an E part and a B part. The gravitational wave affects both the E part and the B part. But again, the E part is dominated by scalar perturbations, so no way to see it. The B part, on the other hand, is good. It's not, there are no scalar perturbations there directly. There is an indirect contribution coming from the fact that, okay, you have your polarization here, which starts in a given way, but around in the middle, there are objects. We make lensing, gravitational lensing, so the path and the polarization is distorted. So the E part of the polarization, which is dominated by the scalar, get leaked, pollutes the B part due to the lensing during the travel from here to here, but not enough, and the shape is different. Okay, this in violet is the polluting part, and in blue it is a prediction for a given gravitational wave background of inflationary origin with different amplitudes. Okay. You see two peaks here. This is the peak I was referring to, the combination. There is another peak because at some point stars are born And the first start ionize again the universe. So there is a period in which there are still 3 ions around. Okay? And so you can repeat the same reasoning that you made here at last scattering surface for this reionized universe with the cis contribution from here, and that makes a second peak, which is a distinctive feature of the signal. And you see, I mean, for some models, this is in principle detectable. This is a projection, not yet. There were, a few years ago, Biceps claimed to have detected that, but it didn't survive more refined analysis. It was noise, but in the future, it is the most promising way to.
They saw polarization, but it was not induced by gravitational waves.
Yeah, it was pollution by foregrounds, etc. It didn't survive analysis. So, okay, this is expected sensitivity for this object. You see the frequency is 10 to minus 17 hertz. I mean, the SN, again, it is very small, it is not that small compared to the 10 to minus 21, but there is F's involved, and if you translate it in the density, it is 10 to minus 16. Okay, so this is it, I think, and it's almost time, I'm late. I thought it was not enough, and again, it was too much. So that is more or less the detectors we have, the sensitivity we have, and on Monday we will discuss the sources and where do they stand. So if you want, I can make a little draw to conclude. Can I raise it somehow? I can switch it off maybe. Yes. But just really to end nothing really. So you have HS and you have overall frequency range. You have somehow LIGO here, AT, and Cosmic Explorer here. You have LISA here somehow. This is 1 Hertz. This is 10 to minus 16 Hertz. You have the pulsar array around here, and you have somewhere the cosmic microwave around here. Of course, if instead of that I will plot you the omega gravitational wave, it will be a different scale, but of course, and we just have to choose one convention. Okay, so this is the situation, the experiments, and there is somewhere also the R-Taylor pulsar around here.
Where is the CMB? CMB is up there.
Yeah, it's up there in this unit, but normally use the other units for CMB, right?
This is only topological.
Exactly. And so on Monday we just study all possible sources and we see where they are or where we're supposed to be. Okay. Is it?
Okay. Let's thank Stefano. Questions also from Zoomland?
Left.
Okay, questions from here?
Past lunchtime.
I mean, just curious.
Yeah.
Pulsar timing arrays use pulsars in
Yeah.
our galaxy. Could we use some kind of same principle as pulsar timing arrays, but using lasers? Or do we have, because they're farther away, but also they're brighter.
But they are not fantastic clocks.
They are not fantastic.
Yeah.
Okay,
The millisecond is
they don't have very.
yeah.
Okay.
They are too erratic. Yeah, too bad.
Okay. So I stop recording now. And go for lunch.
Yep. I must switch this off.